My time hasn't started yet.
No, I've not started the clock yet.
Okay, so yeah, so this project was called Kerchunk Bless You, and the reason it is called Kerchunk Bless You is a bit of a play on words because Kerchunk is really cool, but it sounds like you're sneezing, and it really allows you to do some awesome things. So I haven't actually prepared slides, so we're just going to do a quick walkthrough of the GitHub repo that we've made. So this was a group of people that we collaborated at the Northwest Satellite as well as online. And it was really cool to work with some of the developers at Development Seed and PangeaForge. So what Kerchunk does is it maps the binary structure of NetCDF and other data files such that you can access them directly in S3 in a cloud native way. So there's a little bit of a background here. And the goals were sort of tracked via some GitHub issues and some priorities there. So we sort of looked through the AWS Open data storage and found some data sets that were interesting and then narrowed it down to a particular one, which is a Himawari 8 sea surface temperature. And so we indexed that using Kerchunk into this JSON format and then tried to do some analysis of it. In conjunction with that, we also started creating a PangeaForge recipe. And so in the process of doing that, we identified that Sean identified that there was some bugs. And they were able to get fixed by sort of reaching out through GitHub issues and so on and so forth. So if I just quickly walk through the notebooks, so the first step is once you've got some data files you've found in S3, you've got to sort of look through and work out what the paths are and that type of thing. Then open them up and have a look at the structure of the files. So there's a bit of a list of different dates and times. So this is hourly SST data from a geostationary satellite. But once you get into the data files, you realize that there's some of the names change, the versions change. In this instance, the principal point of the satellite changed and the processing changed. So real world data sets are actually really kind of messy. So it was really great having some other people to go and start to work on the PangeaForge side, which really goes and investigates the data set in a lot more detail. Worked out that there were files missing, versions changed, and ultimately are developing a recipe to try and resolve that and making contact with some of the data providers to get a much more analysis ready data set for general purpose use. And in the process of that, that's where we found the bug where there was something not quite working in the PangeaForge recipe, and then that was able to be resolved this morning. However, I charged on with just using Kerchunk directly, and it's a pretty simple process. For each file, you go and call this single HDF5 to ZAR, which gives a ZAR representation of an individual file, and then you need to join them all together. There's a fair bit of boilerplate code here, but ultimately it calls this multi-ZAR to ZAR function. And once you've done that, you run it out over all the data sets. So I left this running for about a day on the little Jupyter Hub virtual machine just with 2 cores, and it found all the references and then generated a pretty big index, and then they can all be merged together at the end. So once we've got that, I created an intake catalog so that it makes it nice and clean for people to use the data, and it points to the reference set that's been compressed using Z standard, and I've just uploaded that into GitHub so that anyone else can get to it for now. So once you've opened the catalog, all you need to do is this ds equals cat, the name, and then to dask, and you get a data set back. And you can see this data set, it's got all of these variables, but it's got 11,819 time steps. It's the hourly data, and 9,000 lats and longs and 18,000 longitudes. So that's huge. It's 130 terabytes. So that's sort of pretty painful to deal with, but I'm really only interested in a particular region. So I can now just use all the nice Xarray stuff over this big stack of files in S3 to cut it down to a small region. And here's an example region in the Kimberley, and we can click through, and this is dynamically loading the data from S3 now, and we can see the tides moving in and out because it's an area with really large tide range, and there's clouds moving over, and so on and so forth. So now that we've got a data set, we can actually try and do some analysis on actually get to some science. For that, I sort of teamed up a little bit with the GCM filters group, and Nora and Paige helped me understand how to apply and use that library. So I went through and built up a bank of filters which separates the spatial scales of variability in the tracer, and did it in such a way. I'll skip over some of the artifacts, but you can see here that what this has done is here's the low frequency or low wave number, long wavelength variability, and here's the high wavelength variability. And so with a bank of these, we can separate them into sort of long wavelengths and short wavelengths. And then I wanted to look at the time series of that over time. So I used a Dask cluster that thankfully rich signal I got on the Pangeo Forge, the Pangeo call earlier on Wednesday.
Hi, Paul. Sorry to interrupt, but you're over time.
Okay, well, I'll
wrap
stop
it up
there.
quickly. Thanks.
Okay, so but I ended up being able to get a time series of variability at a range of different scales in that particular scene. So that's it. Thanks, everyone.
Fantastic. Thanks, Paul. So next up,